I'm Dr. J, and this is my guide to permutations. As usual, down below in the description, there's a PDF version of these slides. In a previous video, we talked about the basics of counting, or combinatorics, and we discussed 4 basic methods for counting. We discussed combinations, permutations, combinations with replacement, and permutations with replacement. The very last video, we talked about the intuition behind the formula for permutations with replacement. Today, we're going to talk about the formula for permutations without replacement and go through a couple of examples of the formula's use. Now, the fundamental rule of counting says if there are A ways of doing one thing and B ways of doing another thing, then there are A times B ways of doing those two things. Last time, we gave 2 examples that were permutations with replacement. Because we're talking about a topic now without replacement, we're going to give a couple of examples that implement this fundamental rule of counting, but without replacement. The first example is to imagine drawing cards out of a standard deck of cards. So this standard deck of cards has 52 cards in it, that is without jokers. And if you shuffle it up really good, not like I'm doing here, but if you shuffle it up really good, then there are 52 different ways that you can draw that first card. Once you've drawn that first card, there are 51 cards left, and we're doing this without replacement, so this card stays out. Then there are now 51 ways of drawing that second card out of the deck. So if you ask yourself the question, how many different ways are there to draw the first 2 cards out of the deck without replacement? There are 52 times 51 ways of drawing those cards, or about 2,600 ways of drawing the 2 cards. As a second example, we'll consider a Powerball lottery. So the Powerball lottery has 69 white balls and 26 red balls. You start by drawing 5 of those white balls without replacement, and then you draw 1 red ball. And so you ask yourself, how many different Powerball lottery draws are there? You can say, well, how many ways are there to draw the first ball? Well, there's 69. We're doing this without replacement. The balls in the lottery do not go back in the bin to be chosen again. And so we ask ourselves, how many ways are there to draw the second ball? Well, there's 68. Then 67, then 66, then 65, and then we're left to draw that 1 red ball, and there are 26 balls, so there's 26 ways of drawing that red ball. And so if we ask ourselves how many different unique lottery draws are there, we just multiply 69 times 68 times 67, 66, 65 times 26. And we find out that there are quite a number of ways to draw those lottery balls. All right, now we're going to use that fundamental rule of counting in the context of understanding the formula for permutations without replacement. As a reminder, a permutation without replacement is an ordered set of k elements drawn from a set of n elements, but the elements cannot be repeated. And by cannot be repeated, that's how we refer to without replacement. If somebody just says how many permutations are there and they don't specify without replacement, then usually they mean without replacement. Thus, without replacement being put here in parentheses. All right, so we're going to ask ourselves the same question that we asked ourselves in the previous video about permutations with replacement. We're going to say, how many ways are there to choose the first element? Well, since there are n elements of the set we're choosing from, there are n ways of choosing that first element. So there's n. But now we're doing this without replacement. So if we ask ourselves, how many ways are there to choose the second element? Well, one of them is gone, so there are now n-1 ways of choosing that second element. And if you continue this process on, you'll have n-2, then n-3, and so forth, until you get to that last element, that kth element, and you'll ask yourself, well, how many ways are there to choose that kth element? Well, the formula will tell you that there are n minus k plus 1 ways to choose that last element. And that's because that plus 1 is because there's going to end up being n minus k cards left after you choose that kth element. All right, now if we ask ourselves, well, how many ways are there to do the first thing, the second thing, the third thing, the draws, all the way through the kth draw? Well, we can just use the fundamental rule of counting, which tells us that you just have to multiply the different ways of getting the first and second and third and so forth. So we have n times n-1 times n-2 all the way down to n minus k plus 1. It turns out that we can rewrite this formula in a simpler, more succinct syntax. We can write this as n factorial divided by n minus k factorial. As a quick reminder, a factorial is just a multiplication of that integer times 1 less than that integer times 1 less than integer. So the numerator, for instance, is n times n-1 times n-2 times n-3 all the way down to times 2 times 1. And the denominator is n minus k times n minus k minus 1 times n minus k minus 2 times all the way down to 2 times 1. And so that is our formula for permutations without replacement, or simply permutations. Now we're going to give two different examples of using this formula for permutations without replacement. The first is going to be a crossover clinical trial. A crossover clinical trial is when a particular patient in a trial is given different treatments over time. So they'll be given one treatment in the first time period, then a different treatment in the second time period, a different treatment in the third time period, and so forth. So imagine that we have a scenario where there are 3 treatments and each patient receives 2 unique treatments. All right, so this is now a permutation without replacement because order does matter. I didn't specify it before, but order matters in a crossover clinical trial because we might believe that there's a lingering effect from one treatment to the next. So the fact that you had treatment A before treatment B might affect what you see for treatment B. And that's why we're doing the crossover. That's why we pay attention to the ordering. All right, so this is a permutation without replacement, again, because no treatments are the same for a particular individual. There are 3 different treatments, so n is 3, and we're getting to choose 2 of them for our particular treatment plan. And so if you use our formula, the n factorial divided by n minus k factorial, you'll get 3 factorial divided by 3 minus 2 factorial, or 6 different possible treatments in this particular clinical trial. Just to verify this to yourself, you can think about, imagine you label the treatments A, B, and C. Now, you could pause the video right here and determine how many different orderings there are, permutations you will, of size 2 from this set of 3 treatments, right? So I'll give you a hint. The first one is A, B, right? Now pause. And we're back. All right, so the 6 different treatment plans are these: AB, AC, BA, BC, CA, and CB. And so that verifies that, in fact, this formula, at least in this example, seems to be correct. Our second example is shuffling a deck of cards. So we go back to our deck of cards, right here. So our standard deck of cards, and we went back a slide. Our second example is shuffling a deck of cards. And so we can think about just shuffling this deck up, right, using any method that we can do while we're standing up and dropping cards on the floor. And we can shuffle it up. There's the cards. And we can say, well, how many different arrangements of these 52 cards are there? If we say how many different rearrangements, what we're really saying is, all right, we started with 52 cards, and we're going to end up with 52 cards. And the question is, how many different rearrangements of those cards are there? So n is 52, k is 52. It's a permutation because order matters, and it's without replacement because we're not adding any cards. We're just using the cards that we had and taking them one at a time in random order over to this other deck. All right, so we can use our formula. Our formula says it's 52 divided by 52 minus 52 factorial. So that's 52 factorial over 0 factorial. As a quick reminder, 0 factorial is defined to be 1. So then we just have 52 factorial. And we can calculate 52 factorial. It's going to be a big number. It's going to be 10 to approximately 68th power. Now, I want to mention one other thing, because if somebody asks you how many permutations of this are there, usually what they mean is to use all of them, right? So that is that k is equal to n. So we might call that the standard permutation. All right, to wrap things up, we talked today about the fundamental rule of counting. We gave a couple examples without replacement. We then provided some intuition based on that fundamental rule of counting for the formula for permutation without replacement. And the couple examples we gave were of crossover clinical trials and of shuffling cards. In the next video, we're going to be talking about combinations. And this will be combinations without replacement. And this was our second video on a 4-part series. That will be our third video on this 4-part series. If you like this video, feel free to go ahead and subscribe. If you didn't like the video, subscribe anyway. To all of you out there, have a great one.